the Senior Fellow and Senior Director of Process and Specialty Engineering, Head of the Office of Technology at Fluor, and that's missing from your program, it should say Fluor there. And he's going to be talking about coal's triple challenge for air regulation compliance, technology, measurement, and commercialization. Welcome.
Thank you. When I started this, I thought I had a unique topic that no one else would talk about. Ends up that maybe it's a summary of what we've heard, and it's a pleasure and an honor to be here and be part of this program and part of some of the very good talks that we've had. And just kind of want to start out is I grew up in power. I've spent 32 years in air quality control systems development. And in a way, it kind of reminds me of Lord of the Rings. You know, we've started down a path that started more than 40 years ago, before the Clean Air Act, and we've had our first major battle with SO2, and we've done a lot of work on sulfur dioxide to take it from the old units that used to work on multiple small 100-megawatt plants that now we built 800-megawatt plants that handle the flue gas from 3 boilers, and the technology's grown. The second big battle was NOx on the large units that we've tackled, and China is just beginning to work on. England's trying to do SCRs, but they can't find the money. And our next great battle, I guess, is air toxics, and that's a part of my talk today. And I won't mention who the evil one is, but there may or may not be one in this case. But this is a power plant that was built and has been in operation in Texas for about 5 years. It was permitted at that time, and that power plant, of course, could not meet the MATS limits today for mercury and particulate. And that's one of the challenges we have when we start going into the technologies. And I really want to focus on new plants in my discussions here. But if you talk about a new plant and all the regulations are here, of course, CSAPR has come and disappeared like a ghost would. Coal combustion residue is not necessarily an issue on a new plant because you would build and design the plant for that potential 316B. Again, you would design your plant for that, would not be an issue on a new plant. But things like continuous improvement under national ambient air quality standards, greenhouse gas, and MATS certainly are issues. And for those of you who don't go to Texas to look at power plants, I just wanted to show you, just so you know, these little things here are turbines. That's what makes electricity. These medium-sized things here are boilers, and everything else from here back is air quality control systems. This plant is equipped with mercury control, large bag houses, SCRs, and 80-foot diameter wet scrubbers, about 140 feet tall. So somewhere over here, I think that's a truck. So this is 2x800. It's a very large plant. It is a reference that, maybe a perspective that everybody doesn't get every day. We heard some very good talks about mercury, and we know that the limits for mercury on new plants are being revised, and those of us like me who have worked on some of the transition plants under the greenhouse gas laws, I testified under permit hearings, and it's quite an interesting process, but these limits are really a big challenge, and for newer constructed units, I'm hoping the new limits are at least measurable, and can't wait to get those in the next few weeks, I guess, months. Maybe it's by February or March, I guess those limits will be published. And we also heard a lot of things about mercury control options, and I don't know that I need to go into a lot more detail on that, but if you are building a new plant and you're meeting a limit that's anywhere close to where the MATS limits are today, you've got to do everything. I can't imagine that there's any way, because you're looking at 99.7% capture or something of that magnitude. And I think Forrest Gump's mother would say Mercury is as Mercury does, because it's a challenge. We saw a very good presentation from Southern Company yesterday, and the similar sources that's in the regulation under MATS at their sites are not even similar sources. So it's to predict it and to measure it and to guarantee it, you've got to do everything within the process. You've got to understand every variable from gas temperature, the effects of SO3, the effect of NOx capture and ammonia, the removal, re-entrainment, every step of the way in the process. And you've got to do that for every fuel that you may burn or that you might burn or that might show up one day because of the variability of mercury in the fuel, the variability of halogens in the fuels, all the things that are very important from a design standpoint. And when you're doing emission limbos, for mercury, we've gone as low as you can go. You can't get under that bar with, especially when you consider startup, shutdown, transients, and all the issues that are involved with operation of a new plant. Similar is the particulate control issues. Again, the bar is set very, very low. We do expect those limits to come up to be a little bit more reasonable. And there's a bit of good news, I think, in the particulate control arena is people who sail bag houses feel like they can get to those limits under MATS, but they can't guarantee it. I can get there, but I can't guarantee it because I don't know what's going to happen, when a bag's going to tear, what's going to happen in the operation, what's going to happen with fuel variability, what's going to happen with activated carbon injection, and sorbent injection for SO3 controls. But from a conceptual standpoint, is they can get down there, they could probably test it that way, but can you operate it at that really low level for a long period of time is certainly the challenge, and one of the major challenges for particulate control if and when new units are built. And I think we could all debate what's going to be the future of new coal. But I would say that coal is a fuel that's going to be in our energy mix for a long period of time. A program to phase out old coal units and replace them with new coal units makes sense to me. Maybe doesn't make sense to other people, but certainly near MATS limits and higher efficiencies, newer plants, does make a lot of sense. Again, like in mercury, the options for particulate control at these really low levels includes also doing everything and understanding the entire impact from combustion or selection of your fuel, your coal ash mix, the type of fuels, all the way through to the stack. And some of the new units that are permitted, that are transition units, even though the MATS limit says that wet ESP is too expensive, that's most likely part of the process to make sure that you can meet a particulate low limit that is as low as these are under the MATS today. Switching tracks a little bit, there's been a lot of interest in control of HCl, and it's also part of MATS or SO2 as a surrogate under MATS. And I just did a calculation, and I wanted to share that with you, and it's a fairly straightforward calculation to look at the relevant reagent costs for control of SO2 and HCl using various reagents. Limestone being a wet scrubber reagent, dry lime in a circulating dry scrubber or a wet scrubber, and then dry sorbent injection where you choose hydrated lime, trona, or even sodium bicarbonate. And the reason I did this calculation is because a lot of people say, well, this makes sense. I can control HCl or I can control SO2, and there's some pretty high removal efficiencies if you inject enough of this stuff in the gas path. But just from a reality check, look at what it costs you per ton of SO2, and I've made assumptions on stoichiometries of the initial costs of the reagents. But a wet FGD, if you buy limestone at $15 a ton, costs about $25 per ton for SO2 removal. And as you go up for a dry FGD, circulating dry scrubbers, you're in the $63 to $137 a ton. And the dry sorbent injection, because you use a more reactive, more expensive material, it can range from $158 to $994 a ton. And this is just a snapshot of what happens for reagent costs. Many other factors would have to be considered in the selection of what you're going to do as a retrofit on a technology for controlling SO2. You get very similar results with HCl. It's ranges up to $872 a ton. Again, when you use these reagents, you've got to consider the impact of not only removing the acid gas, but you've got to consider what it does to the fly ash, what it does to the ESP if you have one, because it certainly will change the resistivity of the ash and the performance of an ESP, what happens in the fabric filter, and how removing these species might impact mercury control using activated carbon or other chemical additives. So it's a very complicated, but this is just to give you an example of the reagent costs, and I thought it would be of interest to this audience. Measurement, I don't think I'll spend a lot of time on this, but most of us that work in this industry know that it's really difficult to measure some species. And mercury, if you take an uncontrolled unit, 800 megawatts, using a Powder River Basin coal, would emit about 1 pound of mercury a day. So you're going to control that to 99.7% and capture all that. So, and it's below the detection limit of reasonable methods. Well, actually, HCl is the worst of the ones. The limits on HCl is below the detection limits, but mercury is really tough at the low concentrations. Particulate is really tough at the low concentration. It means longer averaging times, longer testing times. So it creates one of the challenges for the industry. Changing, and we've seen this changing pace again, and I'll spend the rest of the presentation on carbon dioxide capture. And we've seen this just this morning, the elephant in the room. Greenhouse gas standards at 1,000 pounds of CO2 per megawatt hour means that a new coal-fired plant would have to remove 40 to 60%, probably closer to 60% for most of them. And that's a challenge amongst itself. It's, and you know, the basis of it is what a natural gas combined cycle unit can do, and I've questioned myself, like, where did that limit come? You know, did people who sell gas decide that that's where it ought to be? I just, I don't understand it, but I do think that moving in the direction, based on a lot of things we've heard, of reducing CO2 emissions, with economic recovery, with load growth, when that begins to happen again, is going to be a challenge. And certainly greenhouse gas emissions for existing plants will be a greater challenge, and definitely for new plants. And what are the issues involved in CO2 capture? Number one, where can you go see a 500 megawatt CO2 capture plant attached to a coal-fired boiler? You can't. You can see demonstrations, you can see small units, but it's just hasn't been fully demonstrated. Now, the greenhouse gas does allow some time for this to happen, but that time is short in terms of the small number of transition plants and what will happen in the future with coal, the other issues that are involved with fuel costs. And we've also heard about the high cost of CO2 capture and compression. And that's got to include CO2 capture, compression in pipelines and the ability to inject it or use it. Very, very complicated, expensive issues. A lot of work is being done in that area. It's a lot of work needs to continue to be done. There's no long-term operation that includes sequestration. All the sequestration work is short-term. EOR has been done for a long term, and we know that works, and it works in certain parts of the country, but that's not long-term storage. That's storage until the oil is gone to the reservoir, and eventually that CO2 comes back up. And there are advancements in technologies, and this is my Fluor advertisement. We have a technology for CO2 capture that we have developed, have built over 25 licenses for flue gas applications. Fluor, by the way, has built over 400 CO2 capture plants, and most of those are on gas sweetening. But our pilot plant in Germany is up and running. Works on coal flue gas at the Wilhelmshaven station in Germany. We're demonstrating advanced solvents, a lot of the things that you'd expect, looking at energy efficiency and improvements in that technology. And it's just one of the technologies that's being developed today. So if I had to summarize the commercial parts of the regulations, and this is just a few of the many, and we all know that this is a challenge. It's a challenge for new coal. It's a challenge for moving forward. You got the higher costs of the coal plants because of environmental controls more stringent versus low-cost gas. It makes the decision-making very difficult. Those of us who've worked in coal all of our lives like high-priced gas. But I do think that the choices have to be what makes sense, and we don't have enough data to know that gas prices will stay low as they have been this summer, and no confidence in that. So it makes those decisions very, very tough. The guarantees without mercury and particulate is not only complicated from a technology standpoint, but it's complicated from how are you going to finance the plant if you don't have that guarantee, and where do you go to get that information? And it's kind of a challenge in that we don't have the data. For example, on mercury, most of the state laws in CAM are kind of steered towards 90% capture, and that's where most of the data has been taken, at 90% capture. There's a lot of data that reports 97, 95, 98, but not day in and day out. So we haven't built the plant that makes the MATS limits, and we can't get the data until we have a plant that's built that makes the MATS limits. So getting to there from a commercial standpoint is a large challenge. And of course, greenhouse gas regulations has a whole nother set of commercial issues. You've got to be able to build it, you've got to be able to capture it. How are you going to run it? What happens when the CO2 plant's down relative to carbon capture? So it means you probably have to over-design so that you do averaging. You've got to have that in your permit. Just on and on. You're losing power production. It's somewhere between, you hear numbers as low as 15%. I think it's really in the low to mid-20s, or maybe as high as 30% parasitic power. If you're capturing 90%, compressing it and sending it down a pipeline a reasonable distance, if that pipeline is 80 or 90 miles, you're going to add even more power, because that's a big cost of the energy of putting down the pipe. And most of us know that the amount of CO2 that's captured at these plants that will have to leave on a pipeline. So you have commercial issues with ownership of the pipeline, maintaining the pipeline, right-of-way things I really don't get involved, liability issues with CO2 from long-term storage. We just really don't know what happens. It makes sense because we store natural gas the way that CO2 would be stored, that you can do it, but natural gas isn't necessarily the same chemical. And natural gas, when it does leak, is lighter than air. CO2, of course, is not. And everything that breathes air in the valley when we have a leak will wish they were not air breathing, or I guess it won't matter to them. This is just a perspective. Fluor did a study for an 800 megawatt power plant. This is actually one of the transition plants that had CO2 capture in it. And I presented this before, but the green stuff here in the back is the power plant, and it goes about as far back as the blue stuff. This little thing back here is a 800 megawatt wet FGD system, and everything in the blue is carbon dioxide capture equipment for an 800 megawatt power plant. And now this is designed as totally air cooled, which makes it take a lot more space because all these air coolers for the 5 heating and cooling circuits that are necessary for CO2 capture are located out, have to consider prevailing winds and some of those issues. And just look, this has 2 about 60-foot diameter CO2 capture absorbers, has these are the air coolers to make sure you have the right temperature coming in. It comes off the FGD into the direct contact cooler. There's another one back over here. All this equipment here is for regenerating the solvent. There's a compressor building, another cooling tower here. So you can see the impact on a plant. This is a new plant. If you tried to retrofit this on an existing plant, like some of them we build SCRs and wet scrubbers that have the Ohio River back there, you just won't be able to get that to happen. And if this plant happened to be close to a location for enhanced oil recovery where they would tie into a pipeline if and when this was built, that's an advantage that they have for this location. It's not an advantage that you'd have other places in the country. It's a lot of equipment that gets added in, and because of all this equipment and moving this out, is part of that is what causes the penalty is the electrical loss of compression, but you also have energy penalties due to regenerating the solvent, reusing the solvent. Again, I thought this would be of interest. Not everybody has seen what a 800 megawatt CO2 capture plant might look like. This is a plant, by the way, that Fluor has guaranteed CO2 capture removal and has made a commercial offer on. So, what are the conclusions? Well, the future of coal-fired electric generations in the United States is uncertain. Have I heard that before? And that probably goes without saying. I always think of coal as, if coal becomes diamond with enough pressure and enough time, and we certainly have so much pressure on coal right now, all we need is the time. So we need the time to figure it out, and maybe it can still be the diamond. I heard today there's other uses, but really I think we're positioned in the United States with maybe a large quantity of readily available natural gas, and when we have a road, kind of like the Lord of the Rings, that we're headed from a regulation standpoint, we're just entering the gates of Mordor, but from a economic recovery standpoint, the road could be paved by making prudent decisions in the energy sector. If coal is going to be phased out, let's not have a war on coal. Let's figure out a way to phase it out over a period of time that makes sense. If natural gas is the right fuel, let's move in that path. If nuclear is right, we've got to remove the barriers as an industry. And I know not many of us in this room can make those decisions, but I always sit back and say, well, let's do what makes sense. MATs and greenhouse gases are a really large challenge. If greenhouse gas regulations become part of existing plants, it not only affects, and it's similar to what's in the proposed regulations, it not only affects coal plants, but it affects a lot of other fuels, affects simple cycle natural gas, because simple cycle natural gas would have to reduce CO2. So it's a lot of challenges in terms of what's happening. And I think we have spent a lot of time in this conference talking about these subjects. All I can do is reinforce that let's move ahead. Let's do something that makes sense. We have a lot of dates. We have a lot of political pressure, and let's find a solution that makes sense to all of us. And I will entertain questions if there are any.
Questions, please.
Could you relate an approximate cost of what you're predicting for that CO2 capture on that 800 megawatt unit? Is there a ballpark?
Well, you know, it's interesting, but it costs less than the 250 megawatt unit that we heard about earlier today. I don't know the exact number, or I really can't share the exact number, but you're looking at adding CO2 capture plus the pipeline would increase the cost of that power plant by about 50% over what a 800 megawatt coal plant would cost. And there's a lot of things that go into it. The advantage of this is it would be, if it was built at the same time as the plant, it's a lower cost than if it was a retrofit added onto an existing plant.
Other questions?
Very good. Thank you.
Thank you very much. Okay, we're going to hear now from our Department of Energy colleague, once the graphics get set up. Tom Sarkus is the Division Director at US-DOE, and he's going to be talking about their very important program on CCS technologies.
Good afternoon. I work for the Department of Energy at NETL, and probably the best or easiest way for me to describe what I do is I'm the major demonstrations guru at NETL. I've worked in the major demonstrations program since it began. At NETL, we cover a lot of areas, as many of you know. We have a strategic center for oil and gas. We have a project management center, which is sort of a code word or buzzword, if you will, for assistance that we provide on energy efficiency, energy infrastructure, and renewable energy projects. But probably our main plank at NETL is the Strategic Center for Coal, and I work in that area. There are about 1,600 projects funded through NETL. Needless to say, I do not have an encyclopedic knowledge of all those projects. There are 600 that are managed by the Strategic Center for Coal. The ones that I work on are, quite frankly, the 8 largest commercial scale demonstrations. And our R&D areas are sort of compartmentalized, that may be a bad word, by technology area. You have gasification, fuel cells, advanced turbines, sequestration, carbon capture. And when you get to the large commercial scale demonstrations, integration becomes a big issue. Funding and financing becomes a big issue because the private sector or non-federal contribution becomes much greater. I'm very proud of the history that we have developed in the program. We demonstrated scrubbers in the 1990s at NIPSCO's Bailey Station, the CT-121 at Georgia Power Plant Yates. the shoe scrubber at Cayuga up in New York. Low NOx technologies included low NOx burners, SNCR, reburning, SCR. And down on the bottom are 3 of our largest projects, which include the 2 operating IGCC plants in the United States. And next year there will be a 3rd when Duke's Edwardsport plant starts up. The department is not participating in that one. And also a large CFB at Jacksonville. These 3 projects were all pretty big in the construction phases, with construction maxing out or peaking probably in the neighborhood of 1,200 to 2,000 people on each of those 3 projects that are pictured in the lower right-hand corner. We're no longer focused on acid rain, and all of our demos now have a requirement to do CCUS. CCUS being a term that is developed by the Assistant Secretary for Fossil Energy at DOE, Chuck McConnell, and we came to that, we arrived at that as a recognition that I think we knew even before the term came out that the many early adopters would rely upon the economics proffered by enhanced oil recovery. But I'll talk a little bit more about that later. But it's a recognition, again, more of the marketplace realities, if you will, than a policy shift. I'm going to go through these in sort of segments, and we have 3 IGCC projects that will do CO2 capture. None of the IGCC projects currently in operation capture CO2. The first one to do that will be Kemper County in 2014. And then we have 2 polygeneration plants and 1 post-combustion capture on an existing coal-fired unit. I'm going to talk briefly about 3 industrial CCS projects that we have. You know, the CO2 molecule, I don't think it really behaves differently or cares if it results from coal combustion, coal gasification, or some other industrial process. But we still can learn from, you know, how to integrate processes, and quite frankly, when you look at some of the costs that can come out of these, some of these industrial processes, certainly not all of them, the costs can be very attractive. And then I'll try to talk briefly, very quickly, because I don't like to say too much, about FutureGen, which is a project I've been working on since 2005. All right. The 3 IGCC projects are shown here, again, with their costs. The DOE contributions, I think, are significant, but in these cases, in every one of these cases, they're dwarfed by what the private sector has to bring. We're simply providing a measure of assistance. A little more information on the processes, including the CO2 capture technology. At Kemper, they'll be using Selexol, and Rectisol will be used at the Texas Clean Energy Project and the Hydrogen Energy California Project. All of them will feed the CO2 into enhanced oil recovery. You see the annual quantities of CO2 that will be stored are on the order of 2.5 to 3 million tons per year. And the estimated start dates, you know, as a project manager, or at least a former federal project manager, I focus on budgets and schedules a lot, and I know that budgets and schedules change as you go through a project. So these are the latest information that I have. Kemper County is going to be a 2x2x1 IGCC configuration, 2 gasifiers, 2 combustion turbines, and 1 steam turbine. 582 megawatts net, and that includes some duct firing on natural gas. It will capture, as Chris Hobson said earlier, approximately 70% of its CO2, and it will be fed into, again, into CO2 pipelines for ultimate disposition in enhanced oil recovery applications. The project is really moving along, and Chris showed a photo before. It's a massive construction project. I mentioned the peaks on the earlier IGCCs. This one, there are presently 3,400 construction workers on site. So it's a really big project, certainly an economic shot in the arm construction-wise, and I think in the future in terms of a reliable source of stable and clean energy for the people in east central Mississippi. Can't say enough good things about this project. We expect it to begin operations in mid-2014. All the offtake agreements are signed. The only other fact I would point out is that this project is so large that they're sinking a new surface lignite mine in Mississippi. So the 3,400 number of jobs doesn't include, because the mine is not really in our scope, but there's another fairly massive effort in creating that new lignite mine to feed the plant. I was asked last night, how do people structure projects? You know, when you structure a big demo like this, it's not unusual for assembly of your project team to take 6 to 12 months. Typically, you have a power plant or a power company host. You may have a technology supplier. In some cases, you can have 3 or 4 technology suppliers. But you usually have one lead technology supplier. You have an A&E or lead engineering company. You could have other entities doing the financing, and you know, you don't just snap your fingers and wish that into place in 2 weeks or 2 months. By the time you run it through that many management chains with legal review and everything else, again, what I've seen is, you know, it's unusual to do that faster than 6 months. And I was asked last night who should lead that. Well, from our perspective, it doesn't really matter. I've seen it managed well with the power company in the lead. I've seen it, you know, Southern Company, an example that I just gave you. This is the 5th demonstration project that Southern has done in our program, and they've managed them all very well. But technology companies can manage these projects as, you know, equally as well. We've dealt with literally all of them: Alstom, Foster Wheeler, Babcock, and Wilcox, and those companies have the ability to lead a project as well. What the Summit project kind of threw a new paradigm, at least to me, into the program is that this is a project developer, and you know, they're there to develop the project, build it, and then to ultimately sell or flip it to someone else. And we've not dealt with that before. We've dealt with a lot of project financing, even the Fortune 500 companies that could, you know, finance projects internally. A lot of times they like to use project financing so it doesn't appear on their balance sheet. So we're familiar with project financing, but not so much with a developer like this. Well, anyway, Summit has developed approximately $7 billion worth of natural gas combined cycle plants in the past. So they're experienced at that. They know how to do that. This is sort of a step up because an IGCC plant with carbon capture and polygeneration is certainly more complicated, a little more difficult, heavier lift to finance and build than an NGCC. This is going to use Siemens gasifiers and power block. It's sited at one of the Future Gen finalist sites near Odessa, Texas. It's a beautiful site. All of those candidate sites were. Another important thing here is, you know, coming from NETL, I'm a researcher, so the concept that's been rattling around the research community for years but never really gained commercial traction until this project hit the radar screen was one called polygeneration. It's had different names. We used to call it an energy plex. And this is a plant that can produce and at least back off a little bit on how much electricity it produces. In order, at times it will produce more electricity, and at other times it will produce more urea or a chemical. Let me be clear, this doesn't swing from 100% electricity to 100% urea, but it can shift the balance a little bit and track those two markets. If urea and fertilizer is bringing a high price on a particular day, well, guess what? The plant will produce a little bit more urea. And the economics of this, if you think about this plant, it's producing 3 saleable projects: electricity, urea, and carbon dioxide, which is fed into a very aggressive market for EOR in West Texas. The market there is, you heard some of the other speakers say they can't get enough CO2. The market there is so active that if a plant that supplies CO2 were to go offline, or an oil field were to go offline and stop accepting CO2 because they had to do some activity, when that I was told when that oil field comes back online, their CO2 supply might not be there anymore. The oil industry, you know, they're just crying out. There's I was going to say insatiable, it probably is not quite insatiable, but there's a very lively demand for CO2. They can't get their hands on enough commodity CO2, but yet in another side of our society, we have CO2 coming out, you know, and creating a perceived problem, and maybe we need to capture that and feed it into the EOR market, at least in the beginning of this CCUS industry. Hydrogen Energy California is also going to follow the polygeneration concept. It's being led by another project development company called SCS Energy, and this they haven't built as many plants as Summit has, but the famous one that is always cited is the Astoria power plant that was built in New York City. So they have a track record as well, and they will be producing, again, a combination of electricity, urea, and CO2. The difference here is that while Summit will be base loaded all of the time, running max out those gasifiers, and you just shift this, you know, whatever, if you need less electricity, you send it to more urea. This one's going to be a little bit more of a load following plant. A very big project, a little farther back. We're looking at a startup in the 2017-2018 timeframe. Both of these projects are still, Summit has completed FEED, HECA is in FEED. They're both still pursuing financial close, and that's what we're trying to hold our breath, cross our fingers, and assist them in any way that we can to get them over the goal line. The one project that we have in post-combustion is at NRG's Parish Station outside of Houston. I believe this is one of the largest fossil energy plants in the country. It has a number of natural gas-fired units as well as coal-fired units. Dennis just mentioned it's going to use an amine-based system, 1.4 million tons of CO2 per year, again being fed into enhanced oil recovery. When this project was proposed to us, it was proposed at 60 megawatts, and you know, assembling the teams takes a lot of time, so you're kind of rushed when you have to submit an application into a DOE funding opportunity announcement. We don't typically give 6 to 12 months for you to assemble your team and prepare things. So when they actually went out and started scoping oil fields that were suitable for this, and the most suitable oil fields for enhanced oil recovery, which is sometimes called tertiary recovery, are those that have already undergone primary oil production and secondary oil production, which would be water or steam flooding, and then tertiary generally refers to CO2 flooding. So you're looking for not just any oil field, you're looking for a fairly mature oil field that has gone through the first two stages of oil field development. Well, when they finally settled on an oil field, they found that they really needed a lot more CO2 to pressurize it and to produce the amount of oil that they wanted to produce. So they scaled the project up to 240 megawatts. They have completed the feed. It's currently under review at DOE, so this part of the project hasn't been approved, but we expect to complete our decision at some point. Frankly, it will not move forward at 60 megawatts because there's no driver with that. There's not enough CO2 to supply that oil field. So we're evaluating it at 240 megawatts, and the revised cost is here, and I believe this is the first time I've shown that revised project cost. The industrial sources, I'm not at liberty to give you dollar figures for what it costs to produce CO2 from these facilities. It's proprietary in each instance. However, it's pretty cheap compared to taking it off of a relatively dilute or CO2 dilute flue gas stream from a power plant. And we refer to these as low-hanging fruit. We have three of them. One is at an Archer Daniels Midland Biofuels plant in Decatur, very pure stream of CO2. All they have to do basically is dehydrate it, and then they have it ready to go into the ground. In Air Products, steam methane reformer, two of their largest in Port Arthur, Texas. Again, the CO2 streams that come off of a steam methane reformer, which produces hydrogen from natural gas, very pure CO2 stream. You don't have to do a lot to it. There it will be fed into enhanced oil recovery. Leucadia Energy has a plan to build a Petcoke to methanol and hydrogen gasification facility in Lake Charles, Louisiana, and as a part of that, they would capture, and if you paid attention to the numbers, if this one gets off the ground, it would be the largest CO2 of the bunch at 4.5 million tons per year. Again, it would go into a pipeline and be used for EOR. A little bit of information on each of those. I'm sure that the conference will distribute my slides, and I won't dwell on these. But a couple of photos of the construction shots. Here's the Air Products project. ADM and Air Products are both in construction. So I can show you, this is fun. As a project manager, construction is always a fun part of the project. And Leucadia is still looking for financial close. They do have their offtake agreements, which is always a pretty key step toward financial close. FutureGen. Now, Dennis showed you sort of the footprint of what's happening or what it would take for an 800 megawatt carbon capture unit on a power plant. And we've learned that on FutureGen as well. FutureGen would be oxy combustion. So our program actually has three planks: IGCC, post-combustion capture for the existing fleet, and then oxy combustion with FutureGen. Let me say that I don't really predict that all 8 of these projects are going to be built, and I would resist handicapping or trying to handicap which ones are going to make it across the finish line. In the first Clean Coal Technology Demonstration Program, we received a large number of proposals, and we ultimately selected competitively 60 proposals for funding. Of those 60 that we selected, we signed cooperative agreements with 50 of them. Of those 50, 33 of them proceeded to completion. So I can't really predict which of these are going to are going to make it there. But what we try to do with each one is take the project through stages so that even if a project doesn't go forward, we gain some knowledge from it. And we're gaining a lot of knowledge learning the steps. How do you find a site for where you want to do carbon capture, or arguably more importantly, sequester the carbon in the ground? How do you deal with the compression and transportation issues? How do you learn about the geology? Let me say that if any of your companies, and Southern Company already knows this, but if any of your companies builds and ultimately winds up operating an IGCC plant, it's a given that your company will become much more involved in chemical engineering than you are today. It's not to say you're not doing chemical engineering today, but you will have at least a part of that plant will be a chemical process plant. And however you choose to do that, you can staff internally, develop and train staff internally, which is what Southern Company has done. You could hire externally, which is what American Electric Power did. They hired a unit of people away from the chemical company UOP, or you could do a hybrid. You could farm it out or contract it or something. With these sequestration projects, I'll go one step farther. If you get involved in this area of the business, not only might you be doing more chemical process things, you will be doing more geological things too. And you really need to get professional geologists on board and not try to do it, haphazardly, or to just go to the local college and talk to the professor, can we sequester in our area? You need to get a lot more involved in that, and the characterization can be expensive. On FutureGen, we drilled a characterization well late last year and early this year. That well cost us $8 million. We're performing characterization studies that are giving us good geologic information in this part of Illinois. So really, whether this project goes forward or not, we've gained a lot of information on how you site a project, how you structure a project, and how you perform the geological characterization activities. With that, I'm often asked to, where do I think things are going? Well, I hear people talk a lot about IGCC, and there's a lot of speculation, but we only have 6 units operating that were designed to use coal, so it's not like there are a lot of them. And my prediction is that when and if we achieve the point where there are 20 of these or 30 of these, that industry and your assessment of whether IGCC is real or good or bad is going to be different than it is today because it is so nascent. Polygeneration, again, we in the research community and the academic communities have liked it for a long time. It will be wonderful to see it in commercial application and to see it hopefully succeed in commercial application. Enhanced oil recovery, we haven't talked a whole lot about geology here, but I use old numbers of, with advanced technology, 80 to 90 billion barrels of recoverable oil in the United States. I always ask people, crunch the numbers, please. The new estimate that came out of NETL ups that upper limit to 137 billion. So one of my bosses once came to me and asked, he said, Tom, what do you think the price of oil is going to be 20 years from now? And I had to give him an answer. And so what do? You guess. And you look at what it is today. It's what, $86 a barrel. And we'll have less oil. Is it unrealistic to think that it might be priced at $100 a barrel for the next 20 years? Recognizing there's a high degree of price volatility there. Is that unrealistic? And I don't think it is. If you use that number on the numbers I just gave you for the amount of oil that we could produce, you're talking a 10 to 12 trillion dollar oil opportunity for the United States. And if you even crunch this a little farther, and I know I'm going to be getting a little spacey here, the oil that's coming out of some of these, the CO2 that's coming out of some of these plants at 3 million tons a year, at 100, figure, what's $100? Oh, I haven't given you a data point. In West Texas, every ton of CO2 that's injected into the mature oil fields recovers over 3 barrels of oil. Over 3 barrels of oil for every ton of CO2. Let's be conservative. Let's take that down to 3 or take it down to 2. But they're getting over 3 barrels. So for every ton of CO2 at $100 a barrel, you're getting $200 to $300 worth of oil. And if you're cranking out 3 million tons of CO2 a year, and you could feed that into oil fields and produce, 6 to 9 million barrels of oil per year and sell that for $100 a barrel, you could essentially pay for your plant. Now, I throw that around to a lot of audiences like this, and I get, oh, but we're a regulated utility. We need to start thinking out of the box as a nation as to how we solve this problem of CO2 emissions and at the same time solve the problem that the oil industry can't get its hands on enough CO2. So with that, I've probably overrun my time and appreciate your patience, and if we don't have time for questions, I'm here to the end of the day.
I think we have time for a question or two. Questions?
About how many years of advanced oil recovery do you think the storage they have before, because you build it, but after a while, I think I've heard you talk before, and you said that there's a limit to that.
Enhanced oil recovery is not the panacea. It's a huge opportunity, and last year I was asked a different question by a graduate student in Illinois, and he said, okay, let's say we can take advantage of this oil opportunity. How long will that industry last? And we're thinking you would stretch that over 20 to 50 years. But that's not the question the way you posed it. The way you posed it was, I believe, if I took all of the CO2 that we have to capture from all of the power plants and inject it into the oil fields, how many years of capacity can those oil fields consume? And you would also have some gas fields as well. The number's a little bit fluid, but it probably ranges from 3 to 4 years to 10 years at most. So EOR is a great economic opportunity, but long term, you want to look to saline fields, which have hundreds, and by some estimates, thousands. It could take all the CO2 for hundreds or thousands of years, and we simply don't have enough coal to produce that much CO2.
One more question?
Thank you again.
Thank you very much. Let's introduce ourselves to Devin Shaw, Sales Manager for CO2 and Power, CSAPR Technologies. He's going to talk about an alternative approach for carbon capture and sequestration projects.
That's the one. Good afternoon. I understand I'm between you and a break, so I'll try and get through this as quickly as I can. I need to advance that. So the topic of this presentation, I thought I'd do a little different than I normally do. Normally I come up, try and pay the company's bills by promoting the technology and trying to sell it. I decided this time, given the room here, I'd probably have a better chance of maybe explaining my own personal opinion on how we can get some of these projects maybe off the ground. What Tom came up and just explained is a really nice success story of a lot of projects that have a good potential to go forward and have gone forward. But what he didn't show is a list of the projects that have failed in getting to that stage, which I think would take probably another 2 or 3 days to get through. It's just a huge list. So just bear in mind, this is my own opinion and by no means is the opinion of Shell, who is, of course, my owner. So the agenda, I'll bring you through a quick brief. Likely most of you don't know who we are, so I'll let you know about that. And then a quick look at what we've done, and then get into the discussion I want to have on the challenges in the CCS projects we have today. Why are they so hard to get off the ground? And then maybe discuss a different approach that might get some of these projects to that important FID, the financial investment decision. So who are we? So we're basically a technology provider. We're a bunch of gas treaters founded the technology back in 1997 and commercialized it to commercialize post-combustion SO2 scrubbing. So you've heard a lot about wet FGDs. Well, we're a certain niche kind of FGD that uses an amine to remove sulfur dioxide from your flue gas. We have experience with regenerable amines. We're actually the pioneers of using amines in oxidative environments. Amines have been used for 80 to 100 years in the oil and gas industry, of course, but that's primarily in cleaning gas streams that are non-oxidative because they're pre-combustion. So we took that, adapted it, and applied it as a retrofit on a post-combustion. So we have a track record of delivering these plants around the world and adapted the technology back basically to its natural fit, which is to capture CO2. H2S is the same thing for CO2 for me because I talk in pH and chemistry. So we basically readapted the process, and we now offer those two technologies, CO2 and SO2 capture. We've successfully commercialized the technology to the point where it became attractive to Shell Global Solutions, and in 2008 they purchased us. We're now a fully owned subsidiary of Shell. So we still operate as an independent company, but we're fully owned by Shell, so I get the best of both worlds. Huge resources, but still the ability kind of to adapt in a project. Also gives me synergistic learnings. That's a big one. Shell's involved in extracting oil, so EOR, and as well operating these type of plants around the world. And believe it or not, Shell's actually one of the biggest companies in the world investing in CO2 capture projects as well. They also deal with a whole lot of sulfur dioxide, so it fits really nicely. So again, as I mentioned, we offer SO2 and CO2 technologies, and of course, because they're almost identical, as I'll show you, we can integrate the two. So actually, usually at this point in a conference, day 2 in the afternoon, I skip right through the flow sheets because you've seen it 100 times. But I think I'm the first one to actually show this flow sheet. It's a different type of conference. So for the sake of the people who have no idea what I'm talking about, I'll briefly run through the technology here. So flue gas is obviously stack gas, anything that currently goes to stack now. We take this gas into the bottom of our absorber tower, which in this case, when I'm talking SO2, it needs to be wet, so obviously we've got some kind of a pre-scrubber section here that basically means you pour water on it and saturate the gas. Once it's saturated, it passes through into mass transfer packing and absorbs SO2. So liquid solvent is poured in the top of the tower and passes countercurrently against the hot rising flue gas. There's a chemical reaction, and the absorbent absorbs the SO2 and comes out the bottom of the tower here, and it's pumped along to another section. So out the top here, you're going to have the removed SO2, so 99.99% removed if you want, or whatever your emission law requires. The amine, which is now loaded up with SO2, will cross on a heat exchanger to recover some energy, but eventually transfers over to a stripper column. This is basically a column where the liquid is dumped in, and it flows down countercurrently against hot rising steam. That steam serves to liberate the bond that was created, so the pure SO2 is released, and the solvent is now empty, so it doesn't have SO2 anymore. We call that lean, and it's used again to go over and over and over, so hence regenerable technology. So that gives extremely high removal rates and allows you to eliminate the use of reagents like limestone and waste products like gypsum, or even handling of gypsum. So if I take you into my CO2 technology, you'll probably notice it's exactly the same, and that's because it's exactly the same. The process is identical, we're just talking about a different chemical. We basically operate in a different pH, and there's a whole lot more of it. So these systems are much bigger, but the flow sheet is the same. There's a little tweak here that's called an intercooling section. Very easy. The heat of reaction of CO2 absorbing into the solvent is much higher than it is in SO2, and also there's a lot more of it. That creates heat in the system. We don't like that. We want to cool it down and maintain a uniform temperature. But other than that, basically the same thing. SO2 stripping, we use steam, liberates the CO2, and this goes off to compression and eventually, hopefully, EOR or to a saline aquifer for sequestration. So in a very quick summary, simplified, that's the technology. If you have any questions on that, you can run through and either catch me after or ask me. But this is a quick example of some of the things we've done. Our biggest flagship project right now is the CSAPR project in Canada. This is a 150 megawatt integrated CO2 capture system. So it's in construction right now. You can see this is actually quite old. I've got a better one coming up. But it's I think right now it's the largest in the world in construction on post-combustion. A lot of others, as Tom mentioned, have reached FEED, but are waiting for that FID, financial investment. And these guys have made it, so they're pioneers themselves, and we're happy to come along with them, obviously. Here it's 1 million tons a day, full 90% capture. It's a fully guaranteed plant, which means it will deliver the CO2 for EOR, which is required by contract. They've also done a smart thing, which is develop an alternate CO2 sequestration point. On site, they have an area to sequester CO2 in case the EOR contracts either go belly up or they choose to capture more CO2 than they have a contract for. I was actually in Saskatchewan when they reached 2,500 miles of drilling for the site, which is the deepest hole in Canada, I think, right now. So the SO2 is actually going to be removed using our technology, converted to sulfuric acid, and sold into the local fertilizer market. And as you can see here, this is actually the base of the tower. It's going to be built out of concrete, and it's 180 feet tall. It's actually complete. It's 180 feet tall, so it's 80 by 80 or 75 by 75 by 180. So we're talking a huge, huge tower. There's some recent towers as well. This is an 8-meter diameter stainless steel. We brought this in on a truck, so it was a big truck, but it was modularized, believe it or not, fully installed. You might recognize this equipment if you've been in any chemical plants at all. They're called steam reboilers. These are the biggest ones they make. There's 5 of them around this, so this is a big plant. Another project we're working on in construction right now is a CO2 capture plant in South Africa. This would be qualified as CCUS because it's for utilization. They actually need the CO2, so they're building a plant to basically to make steam with the natural gas and then capture the CO2 for their own process. A demonstration plant that's currently started up in Aberthaw. This is basically a plant. We built this whole thing in China and shipped it to them, and they installed it. The entire reason for this plant, part 1, is to demonstrate the ability to load follow in the UK. In the UK, coal plants go up and down overnight. We want to prove our plant can follow that load. And part 2, the second year, we're demonstrating our new and improved solvent at 3 megawatt scale, which is the size of this plant. Some other experience, I don't want to spend too much time on here. This is a 1.2 gigawatt coal plant in China. This is a SO2, not CO2 capture, but it just shows, I think I have a picture coming up. This is the tower in construction. Again, concrete. So we have a lot of experience now building huge vessels that are packed, so stainless steel packing inside. And this is 22 meters, and this is one of 2 trains. So these are just gigantic scale towers that we're building, which is what's going to be required for CO2 capture. Another plant in China. This is a project that we just completed a pre-feed study in the UK for CO2 capture. You'll get this presentation. You can look up the list if you so care. All right, so get into the meat of the presentation. So key challenges. Now, before I get in this, I should probably give a disclaimer. I am not, nor do I play on TV, a project execution expert for EPC projects. Maybe Dennis is actually better to talk to from Fluor than I am, but this is just my personal opinion based on projects that I've seen go through to succession and some that have been canceled, and maybe based on those reasons how we could adapt the models that we're so used to using. I'm going to speak mostly of CO2 capture. 2 reasons. That's basically all I know because that's what I'm an expert in. The other reason is, as most of you have heard, the FOAK is a word, first of a kind technology, and when you talk about CO2 capture, that's what we are. This technology is by no means ready for full commercialization. We're in that process now. Everything else has been done. Compression has been done. The EOR has been done. Transportation has been done. Wetting gas has been done. Transporting, everything's been done. So when I focus on the CO2 capture portion, really I'm focusing on the important point that will be relevant here. So if I consider the whole system a jigsaw puzzle, there's different pieces, right? Safety, we really need to confirm at all costs that the thing is safe. Is it going to perform? Are we going to reach the guarantees? How much does it cost? What about scale up? You're going from, as you saw, a dinky little plant to a giant one. What's the OPEX? How much electricity is left going to the grid? How do we have liability? I'm a technology provider. I give you some performance guarantees based on my license. What's that? It's less than 1% of your project. How does that help? Degradation products, so they're not even classified. How do you regulate those? EPC, et cetera, just a whole lot of unknowns. So if I give you an example of a standard approach to project execution that probably most of you are familiar with, you would probably agree that one way to go forward is to select on a lump sum turnkey basis an EPC and have a tender sent out to those individual EPCs, evaluate the quotations, and EPCs use their available data. They provide a firm quote on a lump sum or a reimbursable or a convertible price, whatever it may be, and they stand by their price, and then you select based on your own criteria that you determine you need. Recent examples in CCS, though, have shown that this approach, it doesn't seem to be applicable. So I want to explain why. There's a few challenges that make this possible, or that could potentially describe why. Number one, I'm going to call technology. It's what I just described. It's what everyone else described. These technologies, they're all proven. It's easy stuff, but they're capex intensive. They're extremely large. They take a lot of OpEx. And we talked about this in our workshop roundtable discussion as well many times. Tom just mentioned it again. You're taking mechanical engineers that want to put electrons to the grid, and you're converting them into chemical engineers, basically, and giving them a chemical process. This is new to everybody. So you've basically introduced uncertainty. So the impact on that is the technology partner has to add contingency to account for my own uncertainties. The engineering design has to add margin. And then the industry has no experience at that scale. So if there's no track record and there's no detailed engineering, what happens is the cost goes up, contingency goes way up, and then scope creep happens. So either you end up with a price too small that gets higher, or a price too high and you can't go anywhere anyway. What's another challenge? EPC price. Let's take a look at how we get to an EPC price. Again, I'm not an expert, but usually you got a bank of your engineering data based on previous projects. You got a whole bank of costs that you use. You got relevant projects, and you've got warranty performance history that you can base your guarantees on. And that comes together with your lump sum or your convertible price. We don't have any data here, so we're left with the others, but we don't have any cost. There's no reference plants, and no reference plants means there's no warranty data. So basically, we're left with complete uncertainty when it comes to an EPC price. So that's another challenge that's a little tough to overcome. So the impact is, of course, contingencies are applied. You oversize, you over-engineer. There's a complete, the warranty structure that I want to provide as a technology provider doesn't suit what you want, because you want, of course, the EPC to link the warranties to his price. And this often gives a complete false impression of the real economics of a plant. So what are the third, I guess, challenge would be the contracting strategy. And again, this is linked to the other two, of course. So it's difficult to take an approach that works. Let's say a standard approach for lump sum turnkey would look something like this. A technology provider, a local contractor, they go into the EPC, he wraps them all up nicely and goes to a power company. But my approach is I want to contract directly with the end user and give him a license to do all this stuff. He hands him a BDP that I've given him, and I give him some warranties based on him building it properly. And if he doesn't build it the way I told him he should build it, well, then it's not my problem. So you can see there's a bit of a link here. And the link creates risk. And obviously that creates cost and scope creep, which kills projects. So the impact results in confusion, complication. There's no line of approach. There's no single point of contact. That's finger pointing. We're good at that. And basically the licensing strategy sees the power company has to take on all that risk. First of all, that's always going to be the case. The end user always takes on most of the risk. But we need to somehow create a model that sees some of that risk sharing. So the end result, big time perception of risk. So here's a potential impact. There's two impacts that I think you could fall under any one of these. So number one is the termination before you ever make your financial investment decision. So what could happen is you decide the pre-feed determination, the price is way up here, it's way off the charts, it doesn't match any of your economic models, you cancel the project, and you're happy that you didn't waste your money. But in reality, the actual impact, which is unknown, could be way down here because you haven't actually done enough to be able to know, wait a minute, the price is actually down here, and the gap from here to here is the impact from everything else that I just told you. Another potential impact would be post-FID. And again, this is probably much worse because you've already made your investment. And this is what makes usually the pre-FID cancellation happen, is the fear of this. So you have your pre-FEED predicted, your impact down here, everything lines up nicely, and your EPC that you selected to go forward gives you this number here. But once the project kicks off, you find yourself way up here, and it's not sustainable anymore, so the project dies. So that basically means you might have canceled a project that had a viable life for no reason. So I want to provide some real-life examples, or one anyway. So here's the standard approach. A project in North America, most of these projects have been in either North America or Europe. This was in 2006. They released an RFQ for a new build, 450 megawatt CCS plant. So they did their research, and they did this is an extremely well-educated client as well, so they knew a lot. They have their owner's engineer to support them. But they had done limited engineering up front because, of course, they were limited in cost. So they examined their bids in detail, and they selected their approach. In this case, it was oxy-fuel that they went for. And they launched the project go-ahead in 2006 because it met their expectations. In 2007, the project was completely canceled after FID due to huge CapEx increase because the engineering that wasn't done up front was done here and revealed this was actually not the case, and the scope creep, cost creep killed the project. So what could be an alternative approach? I don't really need to define FEED for you guys, obviously, but it basically gives you a chance, of course, to mitigate these unknowns. And it's a fairly common practice to even do a FEED before you go into an EPC tender. But what's new here that I'm proposing is a multiple competitive FEED procedure. So that's the approach. It basically means you take at least two, maybe three or four. The more the better. Of course, it gets more expensive. You take firms and you have them selected to do paid complete FEED definitions, which includes your EPC tender. So you basically get a bankable number from whoever this proponent is, and the proponent will usually end up being either one party or a team, a consortium. But what you're getting from them is a full FEED development as well as a bankable EPC price. So why do you do this? Not only do you manage your risks, of course, because you're doing the engineering up front, but you're also allowing for the client to be involved in margins, which is when you're managing your own risk because you have to put a number on the table, you internally decide your own margins. If the client is paying for the development, he gets to be involved in what margins go where. And it allows basically a partnership to be built between the EPC and the end user directly. So all that helps in making for a better, at least understanding of a project. Now, why would you do multiple feeds? Of course, project pricing without a feed results in overinflated offers. Even if you do a feed, first of all, if you do a feed and then ask a different EPC to build it, you have the chance that more finger pointing happens because I didn't do the feed, but I'm going strictly on what this feed says. But again, you could potentially end up in the same situation where the EPC contractor takes the feed, gives you a price based on his understanding of that feed, and you select it going forward, and you end up with a project that doesn't match expectations. This multiple feed allows two parties or three parties to compete in a very competitive playing field because you're paying them to. So you're paying them for the work that they're putting in. They're performing the engineering up to, say, 30%, and you're tailoring their offering to you. So it's apple-to-apple comparison. That's the other biggest problem is EPCs give all of their understandings and their quotations, and they're all different understandings and quotations. So then the utility has to decide what means what, how do I level the playing field. So this multiple feed allows for that type of elimination. All those contingencies come off the table. So what it can do is, yes, it increased your costs up front because you have to pay for 2 or 3 potential feeds, which doubles or triples those costs. But it lowers the overall engineering cost because of a competitive environment. Of course, you're sharpening the pencils of the people on the table. If they had too much contingency because they don't feel comfortable, they might lose the job. So you're going to see the best possible price from every party because they're interested in getting that job. Also, schedule-wise, provides the best possible schedule because the party you're selecting performed the feed and is comfortable with the engineering to that 30% level. So you start at 31, you don't start back at 1. So there's no schedule slip, and that you don't have to redo that feed, therefore there's no added cost there. It's mutually beneficial, of course, as well, because the technology and the operating company are now working together, and if we're paid to develop engineering, of course, everybody is going to end up with better. And then in the future, of course, you don't need to do this because we'll have 10, 20, 30 examples, and you can just pick cost data. But until we get there, this approach might be interesting. Here's a real-life example of the competitive environment that I just explained. So in this project, there's a pre-shortlist evaluation, so 7 to 10 proponents were selected, provided detailed bids. Evaluation, the client selected 3 to go forward and paid them to develop full feeds as well as a bankable EPC price, so a lump sum turnkey. Once this was provided from all 3 parties, after being paid to develop all of this, one provider was selected and it went forward into 2 EPC stages. One where all the pre-detailed engineering and long lead item procurement was done, and then a break for financial investment decision, and then of course construction started. So this was exactly what happened, and in the feed, the risk, the analysis, all the mitigations are all taken into that cost, and then you go forward. In this particular case, the project did go forward, and I think I have an example of exactly that. So the expectations, there was public information based on before the information was available, obviously done before the project started, was that the capture plant was going to be about 43% of the projected budget. This is based on information from EPCs as well as capture providers that you get for free in proposals. The actual lump sum turnkey, that's a bankable price and project's almost finished construction, it turns out to be only 35%. So if you look at that gap right there, you more than paid for your multiple feeds right there. So you've got all your money back and then some, and you've got a more efficient project. And to boot, on top of that, the OPEX savings is actually a 30% improvement versus the expectations that were in mind by the utility before the project started. So there's no impact on schedule. The feed engineering was completed up to 35, and then the detailed design started at 35.1 and went forward. So no schedule slip there. I don't need to go through this. Basically, from and to, you can almost see the same thing. So you've basically added one more step, but at project completion, it's this point here that you're trying to get to. So to get to FID, you've got the exact same number of steps, and then you've got one small step here to actually choose the EPC to go forward. And for basically the same schedule, but a lot, as you've seen by that real-life example, you've saved a significant amount of CapEx and obviously eliminated a lot of risk. So now this is basically just so new solutions call for new approaches, and it's basically a conclusion slide that it's a win-win, I think, because it keeps EPCs and technology vendors honest, but also allows you to improve a lot on not only your understanding, but your risk. And if you can mitigate risk, you have the chance of taking a project from a design stage to potentially a construction phase, which is what this project is now. You can see here it's 180 feet tall, SO2 and CO2 in full construction. Compression is over here. You can't see it yet, but this will be started up early next year. Actually, the end of 2013 is the startup date, full operation by 2014. So I think with that, I tried to rush as much as I could. And I'll take any questions you may have.
Questions? I think you're competing with the break.
Very good. Thanks.
Thank you. Okay, it's time for the break, and I think for a half hour, please come on back, and we got 2 more to finish up the day.